Okay, we're going to start the next unit of notes here. Again, I apologize for these not being posted on Monday. Zoom flaked out on me and erased my, or didn't get my recording. So this is the unit on induction, on induced magnetic fields, and this is what corresponds to the concept of capacitors in electricity. So what happens with electromagnetic induction is we are looking at flux. Okay, if you go back and look at the homework notes, I talk about it in there too. But flux is literally the number of field lines passing through the cross section of a surface. And what happens is we can use this to create current flow in something that has no electrical connection to anything else. And the only way that this will happen, though, is the flux has to change over time. All right, and the rate of change determines the amount of current flow. So the only time we have induction is when the process of change is happening. Once the flux stabilizes again, it stops. So if your generator's coil stop turning, the lights go out, for example. Okay, now the figure in your book shows a little bit about this, but there's some figures on this next page that will show you this. So the things you want to look for in these thought experiments is when there's no field, there's no current flows. You have to have a magnetic field. There has to be a change in that flux. So when the field stabilizes, the current drops to zero. The current always flows to try to counteract whatever change we make. The flux wants to stay constant inside that loop, all right? So the field will always flow to try to counteract whatever change you're making in the flux, all right? And the faster that happens, that change happens, the more current flow there is. So if there's a velocity component to this, it's velocity dependent. And it doesn't matter what material is used, all right? So in these pictures, you've got a magnet moving back and forth through a coil, which will cause a change in flux. First, the current flow will happen in one direction as the flux increases, in another direction as it decreases. You have a switch that turns on, okay? And then down here, you have a situation of a transformer where you create current in one coil and cause that to change, and that induces a flow in the second coil. So these are both examples of induction where there's only one coil. That's called self-induction, and the other one is called mutual induction. A choke on an electric motor is an example of self-induction. It keeps, like say, the motor from spinning up too fast and breaking something. And then transformers or generators are examples of mutual induction. So Lenz's law says the loops do not want change to happen. And let me fix this real quick because that doesn't look good. So let me move that down. There we go. Okay, so Lenz's law doesn't give me a value for the induced current. It just tells me which way the current will flow, because loops will try to resist whatever change happens in them, okay? So if the flux is increasing, they will try to do something to decrease by creating a field to cancel out whatever field is in there, all right? So if the flux is increasing, they're going to try to cancel the field. If the flux is decreasing, they're going to try to bump up the field, because that's what they can do, is they can create magnetic field. So that's their only tool to resist the change. So they will either be trying to cancel the field out, or they'll be trying to bolster the field if it's getting weaker, if the flux is causing it to get weaker. So the loop is doing whatever it needs to do with current flow in whatever direction it needs for the flux to stay constant in value. And then once the flux stabilizes, the induced current vanishes. Okay, so if I were to take this magnet and move it toward this loop, as you'll notice in the lab, the electrons are going to flow to try to cancel out that field. So they're going to try to create field going to the right in this picture if the field is getting stronger going to the left. Okay, so what it does is it generates current to use, and in your lab this week, you'll see that. So Lenz's law just tells me about direction. It doesn't tell me about the value. Where I get the value from is from Faraday's law. So these are different examples of what you might see in a Lenz's law situation. You've got a coil rotating in a magnet. That's a generator, okay? You've got a magnet that's where the microphone is moving over the magnet, and that's what happens inside a microphone or inside pickups of an electric guitar, for example. Now, Faraday's law says, and this is another one that got messed up. Fix it. All right, there we go. Okay, so Faraday's law looks at the flux through a loop. All right, so we calculate the magnetic flux through a loop. There's three things it depends on, and we talked about this in the homework notes: the strength of the field, the size of the loop, and the angle between the surface area vector and the magnetic field. So all three of those things help me calculate flux. And flux is measured in units called Webers. Again, look at the homework notes for that. So if the flux changes, the current flow is created according to Lenz's law. So if there's a current flow, there has to be a potential difference, or an EMF, as we learned from the circuits chapter. So the induced current flow makes it seem like there's an EMF that's been induced as well. So that's what Faraday's law actually calculates, is the induced EMF. All right, so we know that current flows from high potential to low potential, so we can actually figure out the polarity of this induced EMF. And the faster this change in flux happens, the more current will be generated. So again, that's why your generator has to spin up to a certain speed for the lights to come on in your house. All right, so there's reasons flux can change. The field can get stronger or weaker. The area of the loop can change, so I can make the loop bigger or smaller, or I can rotate the loop, and I can cause the orientation between those, the A vector and the B vector, to change. Normally you see the first one and the last one a lot more than you see the middle one. So you either have something spinning, which changes the angle, or you have a field that's getting stronger and weaker by moving a magnet back and forth. Okay, if I want more current flow, I just need to have more turns in my loop. I need to have more coils. So Faraday's law says, and we saw this in the homework notes, the negative sign tells me that that's opposing the change in current or in flux. So the negative sign just tells me it's opposing. Now, I don't really need that to calculate EMF. N is the number of turns, and then that's the change in flux over the change in time. Now, sometimes just one of those things will be changing, B or A or the angle. Sometimes it may be all three of them. You don't know. So you have to read it per problem to see what's happening. And then that T is time. So however long it takes for that change to occur. So this creates a situation called inductance, where we have mutual or self-inductance. Different examples of this are generators and transformers. And I worked some problems in the notes on transformers, so you can go to the homework problems and see those. But we see transformers a lot in our day-to-day life because we see them on laptops, we see them in cell phone chargers. You have one outside your house on your power pole. So yeah, so that's pretty much, it's just a little short set of information on inductance. So that's where we'll end that.